All right, guys, as promised, what I'm doing is I'm re-recording those notes that are dealing with the notation as far as right here, as you can see on day 3 of the calendar, okay? So it is 6-8. It's finding antiderivatives and indefinite integrals, basic rules and notation, but more so it's this summation notation while doing it. So this summation notation is talking about specifically these capital letter E's from the first to the nth jump. Okay, so that summation notation is what these notes are going to be talking about. Okay, so I want to give you a quick review so that you can see how you can correlate this to something that you already know. Okay, so the definite integral, that is, are these bounds from A to B. Okay, so we've done these as far as when we take the antiderivative, just so that you can kind of wrap your head around this. The antiderivative of f would give you a capital letter F, and it's f of the final position minus f of the initial position, okay? And this was correlated to where, let's say we had 2 to 3, and it was x squared dx, okay? We've learned recently that we first have to find the antiderivative, which would give us x3 over 3, so x cubed over 3, and its bounds were 2 and 3. So when we plugged in this f of b, it's like plugging in that 3 to get 3 cubed over 3 minus, what would I get if I plugged in the 2 where x was at? So it'd be 2 cubed over 3, okay? So this would be like 27 over 3 minus 8 over 3, and this could give us 19 over 3. So this is a quantitative answer. It is a definite integral still. We're going to get a number answer, no f of x plus c or anything like that, like you do with indefinite integrals. So there are bounds for sure. These bounds are the lower limit of integration and the upper limit of integration. And again, like my example here, I'm going from 2 to 3, okay? This integrand right here is the function, and my example here was x squared. And then again, this just says in respect to x variable, it's the variable of integration. It's that differential piece. And then last but not least, the integral summation sign. So this integration symbol right here, okay, this squiggly thing, if you will, it is the same as this summation here, okay? So again, this summation extends to that summation notation. And then the bounds are going to basically tell you where you're starting and how far you're going to go, okay? So I know it's been a minute since we've seen this, but back when we were doing rectangles and we were doing like the base times the height of each rectangle, and we're adding up all these infinite rectangles together, that's what's happening here, okay? So this right here is f of whatever that value is. All of that is a y value, okay? So it's like saying the height of something, okay? So that's h. And then over here, let's box this, let's say in purple, this is telling you the width, aka the delta x. And if you recall, we did look at an equation that was something like when we did Riemann sums, and they were all the same width as far as if there were multiple rectangles, like we had 4, we had 6, and different rectangles. To get how wide each rectangle's base was, we did the high, so this number here, minus the low, and then we did it over n as far as how many rectangles are we looking at, okay? That's the equation that'll give you that delta x, and that delta x is the base. So this base times the height basically is just one rectangle's area. And we're adding all the rectangles. So we're saying infinite number of rectangles. This would give us eventually the exact answer, which we now deem as a definite integral. Okay, so again, this is the base in purple. And and in blue right here, all of this is the height, so base times height, but not just of the first one, okay, but of all the infinite rectangles. So notice this I is like saying the jump. So right here, this I is saying the first one, the second one, the third one, all the way to the infinite rectangle that you're adding them all up together, okay? So another thing to look at is, where do you start as far as the notation goes? Where do we start as far as what's our first x value, what's our next x value, and what's our first y value, what's our second y value, and so on and so forth. So what I want you to kind of see is, back when we learned y equals mx plus b, b is where we started. So if I were to rewrite this as b plus mx is equal to the y, okay, this y value is what I was trying to show you just moments ago. All of this is the y value. Where we start, this y value, and the change that each jump will occur is showing you where we start is a, and the m is that change per jump. So x is to I as m is to b minus a over n, okay? So this is like delta x, if you will. Each x jump was that I jump, like the first jump, the second jump, the third jump, all the way to the nth jump, which here is saying to the infinite jump, or the infinite rectangle. And then again, this m is just talking about how much is it that you're changing each time, each jump. So starting point is A. This is the change that occurs per ith jump. And all the while, this is the width of our rectangle. So otherwise the base. So base times all of this height, and we're going to add infinite rectangles together. Okay, so let's see what this looks like with our examples. Okay, so looking at this huge parentheses, and let me go ahead and color this in blue. This huge parentheses is giving us our y value, okay? It's giving us our y value and how it changes each jump. So think of this as the height, okay? And this right here, this little piece right here, is just giving us the delta x, okay? We don't necessarily have, in this one, an I showing. Like, it doesn't have the summation symbol saying from the first to the nth, and basically saying infinite number of rectangles. But we can still see the pattern occurring as far as what is our base width, our delta x, and then what is it going to be as far as what are these changing heights as I go on throughout the problem. Okay, so looking at this, this is saying that my first y value is going to be 1 over n squared. Okay, that's where I start. So picture this as, if I have a rectangle, my first one's width is 1 over n, and that comes from this base's this amount. Okay, so that's 1 over n. And that means that we could say that this is, let's say, 0, okay? And this is 1 over n. So if I was looking at this like, here is my x and y axis. My base of the first rectangle, that width is 1 over n. So each jump is 1 over n. That's this delta x right here, the base, the width of the base of each and every one of those. And the function would be plugging in 1 over n, which is that x value right here, and squaring it. So it's almost like it's waiting for an input like x squared, okay? x squared. That's what all these pieces are showing, okay? So we know it's not going to be c because it doesn't have that x squared as far as the y value is concerned. Again, h is for y. All of this is the changing y value. Like this is the first rectangle's y value. This is the second rectangle's y value. This is the third rectangle's y value, all the way to the infinite one, okay? Because this is going to be the infinite y value squared. Okay, and we can say something like that. Okay, so, and I know like when we did Riemann sums, we GCF'd out the same base. That was the same equidistance. If you were to not foil, but distribute this out, it would be like having a bunch of base times heights. Okay, plus the second base times height, plus the third base times height, so on and so forth. All we did here is just take out all the bases by GCFing all those bases out, where you're just looking at the first y value, the second y value, so on and so forth, the third y value, okay? So it's 1 over n is going to be the delta x. And we learned that delta x was b minus a all over n. So if this is delta x and this is delta x, then we could say that b minus a, aka our highest number minus our lowest number, so our high minus the low, has an interval jump of 1. So 0 to infinity, that's not a jump of 1. So we know it's not a, okay? 1 to 2 could work, or 0 to 1 could work, because they both have a jump of 1. Okay, so again, that equation is, let's say a is 1 here, b is 2. The equation for delta x, aka the width of each subinterval that are equal length, is going to be the high minus the low over how many n's you have. Okay, so the high is 2 minus the low of 1 over n. This would have a width of 1 over n per each jump. And that's shown right there, this very first thing here. And it works for B or it works for D, okay? It's all about where you start, though, that will dictate what's going to be your y value when you start, okay? So this one right here immediately started at the function, and it's basically saying that it's not starting at 1, it's starting at 0. Okay, so back up just a little bit, and right here, I had a plus the jump of b minus a over n. Okay, that's like taking this right here and saying it could be 0 plus b minus a over n, and that's going to be quantity squared. So this 0 says you're starting at 0, okay? So that's why it's going to ultimately be, or it's going to be B, it won't be D. Because if you started at 1, what this equation should have been is it should have started at 1 and then add each jump of 1 over n as far as squaring that piece. That would look something like this. All of this would be like x squared, but you're starting at 1. Okay, then you have multiplied by each width, which in this case would be base times this red height, starting at 1. So we didn't start at 1, we started at 0, because it's like, again, 0 plus, there's like an understood 0 right here inside that parentheses, and it's 0 plus 1 over n. Okay, so B would be the answer there. Let's keep looking at others so you can see the pattern a little clearer. Okay, so again, this little 1 over n smidget is going to tell you the width, aka how wide is each of these rectangles. The delta x, okay, that's the delta x, the width. We know that the equation is b minus a over n. Okay, this n does match up with this, and we're going to know that the jump of b minus a, the top minus the bottom, will have a jump of 1. So 2 minus 1, that satisfies it. This one satisfies it. 1 minus 0 satisfies it. And 1 minus 0 satisfies it. All of them show a jump of 1. But the difference here is you're going to see a pattern. It's like 1 over something. So all of this it can be seen as this is all over x. This is all over x. This is all over x. And this is all over x. Okay? So it's not going to be b, nor is it going to be c, because it's a 1 over x function. Okay? And now what we're going to do is we're going to show you starting at 1, we're going to do this 1 over x jump. So this one starts at 0, so it is not D. This one starts at 1, it's going to be A. Okay, so let me show you with color highlights. Starting at 1, we have a 1 over x change throughout all of this. That's my function. The width was a constant 1 over n, and that width, it's not really drawn there, but that's like the infinitesimal width, that infinitely small width as it approaches 0. Okay, so as this n approaches infinity, 1 divided by infinity will make that approach 0. Okay, and last but not least, this 1 up top that we got from b minus a shows that starting from this 1, we're going to have a jump of 1 total. So 1 to 2 would give you that jump. That's why A is the answer. Okay, let's keep looking at them because there are patterns. You just have to see them. Okay, so this one it didn't copy over well. It should be just the integral of sine of x in respect to x, starting from pi over 2, going all the way to 3 pi over 2. Okay, and if I looked at these, I want to find something like this y equals mx plus b that I first started the notes off with, as far as it'll start at b and it'll have a jump for each change. So what is this b plus something? Well, this b says where you're going to start. Your lower bound is what this b is representing. So you're going to start at pi over 2. And notice this one shows a starting value at pi over 2, as well as D does. These don't show that starting value, so you know it's not going to be those. Okay, so starting at pi over 2, the function is sine of x. All of that is sine of x. Okay, and that's what you see here. The width of each jump is here, but the way we show that width is b minus a over n. Your b value is the top bound, which is 3 pi over 2, minus the lower bound, which is pi over 2, and it's over n. So 3 pi minus pi is 2 pi over 2, which would cancel, and you're left with pi over n, which is this width right here. Pi over n is each width of what I'm looking at as far as each of these rectangles. Okay, so this pi over n is this width right here, this delta x. And again, we got that from b minus a all over n. And it simplifies to this. It doesn't simplify to 1 over n. Okay, because if it did, that means the jump from pi over 2 to 3 pi over 2 would be 1. Okay, but the jump from pi over 2 to 3 pi over 2, it isn't 1. It's 3 pi over 2 minus pi over 2, which is going to be 2 pi over 2, which reduces to pi. Okay, so that shows that this is a jump of pi for each n rectangle. Okay, so this right here, A, would be the answer. This didn't show that it had a jump of pi each width. All right, so I think we're starting to get this. And it all really ties into this b plus mx that I was showing you of how you can interpret where it starts, okay? Let's look at this one. Again, formatting, this should have been from 0 to 4 of x cubed dx. So let's look at the pattern. We start at 0. So all of these, they start at 0. So the y value is like 0 plus this 4 over n cubed, 0 plus this I over n cubed, 0 plus this 4i over n cubed, and 0 plus this 4i over n cubed. Okay, so they all start at 0. And we have to ask ourselves, what's the delta x? What's the high minus the low over n? Here, it's 4 minus minus 0, that is, over n. So 4 over n is the width of each of those rectangles, okay? You know it's not going to be c because that's not 4 over n, okay? Over here, this 4 over n was with the cubed, aka the function or the y value, aka the f of x integrand. So it's like x cubed. It's not here because 4 over n needs to be the width, okay? Over here, this is the width and this is the width. So right now we know it could either be b or d, okay? Because this is the base value, otherwise the delta x width of the base. And the function is the function is y equals x cubed. So this entire height, so again, base times height, this height is the y value, okay? And therefore it's x cubed. So it's a pattern cubed, okay? So this one, they both have a pattern cubed. It's all about what is it for that first piece. If I start at 0, what will I get? Okay, as far as like what y value am I going to end up putting in? So if I start at 0, let me go ahead and like draw you an x and a y axis. And if I were to start at 0, and each jump is going to be 4 over n, that means this, it would be 4 over n. The next one would be another 4 over n, otherwise 2 of those jumps, so it'd be 8 over n. The third one would be 3 of these jumps. So these aren't like mixed fractions. You're multiplying 2 times 4 over n, 3 times 4 over n. These will show you each jump, what would the y value be, okay? So right here is saying that if I put I as 1, then that means it jumped 4 over n over, and then we cube it to see what would that y value be. When I is 2, then it will be 8 over n. So we're going to jump 2 jumps because that's 8 over n. And what would the y value there be? Okay, so that's why it's going to be D on this one, because it tells you and it shows you this like graph right here is a good way to see it. We started at 0. Each jump was by 4 over n. So the first y value will be what is f of 4 over n, but cubed, okay? Because the function is an input cubed, okay? So the second one would be 8 over n, because you jumped another 4 over n over, okay? So each width is 4 over n. And the only one that shows you this is D, because the first one would be plug in this I, or this number 1 in for I, you get 4 over n, which is that one right here. When I is 2, you would get 8 over n, which is that second y value right here. So that one would give you something cubed, gives you a point. Something cubed gives you the other point, okay? If you did that over here, you wouldn't get that. You would get 1 over n for the first jump, and you would get 2 over n for the second jump. And that doesn't make sense because you're jumping by 4 over n each time to get the next y value, to get the next y value. So that's why D would be the answer for that one. All right, so now let's look at this again. Base times height is what we're looking for. This 1 over n all by itself is either going to be a base or it's going to be a height. Okay, the one that's smaller tends to be the one that's the base. So this is your b, aka your delta x. And then the one that's way more involved, like a function would be, h is that y value, aka f of x. So your integrand function comes from this. And you can kind of see like a 2 parentheses squared plus something. Okay? All of these have 2 parentheses squared, like a 2x squared plus something. So we got to ask ourselves, is it going to be adding x each jump? Or is it just going to be adding 1 each jump? Okay? The fact that we know that this I over n represents x, because it's like 2x squared on all 4 of these, then we know I over n here is also x. So it should be A or C, not this constant of 1. Because if I plug in 1 for I, I'd have 1 over n. If I plug in 2 for I have 2 over n. It doesn't remain just 1. If it was a constant, there would not be this I there. It would just be plus 1. Okay? But it's changing every jump. That's why we have this I over n shown as x. Okay, so now these are just summation symbols. Again, it's just the formatting on the PDF. It glitched a little bit when it copied over. Okay, so we got to ask ourselves, where are we starting and how big is the jump? If B is the width of each of these rectangles, so this is my width, and we know it's delta x, then delta x is b minus a over n. This delta x says that it's 1 over n. Therefore, b minus a needs to equal 1 for that to happen. Okay, because you see those n's match up. So b minus a should be a jump of 1. Well, from 1 to 2 is a jump of 1. From 0 to 1 is a jump of 1. We just have to ask ourselves, where exactly is it that we're starting? Are we starting at 0 or are we starting at 1? Okay. So this one's a little bit different because it has this extra plus I over n. And that right there, again, was this x. So right here, the way you can see is where you would start is it's secretly showing this. So 2I over n. This is like going to be squared. And then plus an I over n jump each specific x value. Okay? So it's like going to start at 0, and it will go up by this 2I over n quantity, or that's p squared, and then plus this x here. Okay, so 2x squared plus x, but there's no constant here. That's why it's not going to start at 1. Otherwise, it would be 1 plus 2I over n quantity squared, and so on and so forth. It would go from that. Okay, so I just want to make sure that you understood that this one would actually be C, because it's not starting at 1, it's starting at 0. Okay, and we saw other examples like that as far as if they start at 0 versus if they start at 1. Okay, so like this one right here started at 0, and this one up here show that it started at pi over 2 because it was like that constant plus the integer jump. Okay, so that I showed you that integer jump, that term, that first term, the second term, the third term, and this constant all by itself, very, very similarly correlated to this b plus mx field, would show that it starts somewhere. Okay, it starts at a constant. So that b plus mx, these are x, that's x, so it's like the whole thing is x, or that mx representation. There's no plus b. So it's like saying this whole thing is like mx, not bx. but there's no b that it's saying that it starts from. Okay, so make sure that you understand that that would be 0 for that one. All right, so let's do another one. So all of this is the y value, aka the height, okay, aka the function f of x, the integrand. So we have 2 over 2 plus something squared. So 2 over 2 plus something squared. So it's not going to be this one. It'll be 2 over 2 plus something squared. It could be b. It's not going to be d because it doesn't have this constant on the bottom. And it'll be 2 over 2 plus something squared. So it could be b or c right now. Okay? Now, this tells you that how much is each jump. Okay, so delta x is 2 over n. We know delta x, again, is the high minus the low over n. So b minus a has to equal 2. Okay, look at this. This jump is only 1 away. We need this to equal that. So from 0 to 2 shows a jump of 2 that we need. So b is our answer. Okay, that shows you 0 to 2 is that jump of 2, each jump of n. And then all of this in red, as far as the function is concerned, is showing you the integrand itself. 2 over 2 plus something. This is like that something squared. Okay. All right. So now let's move on to the last things for this video. Okay. These are basically just matching up what we have as far as some example problems. And we're going to see what are the answers that it would equal. Basically, what would it mimic? What would it look like? Okay. So just more examples of what we just did, only now we're going to actually see what patterns there are amongst all these 10 problems. Okay, all right, so here we go. And normally what we would have done in class is we would have actually cut these out like cards, and all you were going to do was match them up. Okay, so you have 1, 2, 3 all the way to 10, and then you have A, B, C all the way to J. And all you're going to do is just match which one goes with what. Okay, for instance, let's find which one of these alphabet letters goes with this first definite integral number 1. Okay, the answer is actually G. Okay, so 1, the answer is G. And the reason why is because, here we go, this 4 over n is the delta x of b minus a over n. The ends match up, and we know the interval jump is by 4. So from 0 to 4, that checks out. Okay. All we're going to do now is look at the rest of our function, and we're going to see like everywhere we see these eyes at, it's like the each jump, if you will. Okay, so it's like the jump that we were saying over here, but this is like the stuff squared. So x squared plus 9 underneath the square root matches up with this one right here, and that's how G matches up with number 1. Okay, the next ones that we can match up are 2 matches up with C. Because look, the jump is by 4, which 1 to 5 is a jump of 4, and it's 1 plus the something squared. So all of this entire thing can be seen as x squared plus 9, which is what we have. Remember, this 1 just tells you that it's going to start at 1. So it wouldn't be like 0 to 4, which would still have a jump of 4. It would start at 1. This is this b plus mx feel to it of showing you that it will start at 1 as its lower limit of integration. All right, so let's do number 3. 3 matches up with J. Let's go look at J. Okay, so I'm going to actually have to move that over. All right, so J says 4 over n is the jump. Okay, so it's going to have a jump of 4. 1 to 5 is a jump of 4. We're going to start at 1, which makes sense. We started at 1. And it's going to be all of this squared plus 9, which is exactly what we have over here. Okay, so let's keep going through these. Number 4 is going to match with F. Okay, so looking at F, let me move this back down. All right, so the jump is by 4 that you see right here. And that was the jump of 4. And it's like, again, multiplication with the I is like all of this is X, okay? But because there's a constant here, it's going to be 2X plus 9, okay? So 2X plus 9. So I'll show you one more time. Here, just like on one of the ones that we did from before, it kind of looked like this. It's 2 times the stuff, aka 2X. But because you're starting at 0, you can interpret this as 0 plus this, okay? And then at the very end, you're going to do plus 9. That doesn't mean that it's starting at 9. It means that there's a constant of 9 here. And there's an understood 0 that belongs right here that shows it's going to start at 0, okay? And again, these will be multiple choice on the quiz and on the test, so they're a little bit easier to interpret and kind of compare and contrast. All right, so let's look at 5. 5, the answer is I. So right here, let me move this one more time. The jump is by 2. And sure enough, on 5, there's a jump of 2. This is not multiplying by the I piece, so it's not like 2x like the previous one was. This will be starting at 2, which is what this shows. And then it'll be, this is x squared plus 9. So x squared plus 9 is your integrand, aka your height or your f of x function. All right, so let's do these last ones. So 6 is h, 7 is a, 8 is b, 9 is d, and 10 is e. Okay, so let's look at h first. The jump is by 4. Yep. There's an understood 0 plus that I jump. Okay, so it's going to start at 0. Yes, it does. And it's something squared plus 9. Something squared plus 9. And you get h as far as being the answer for number 6. A is the answer for 7. The jump is by 4. Yes, we have that. It starts at 1. Okay, so the way we were seeing this, my mistake on this, some of you probably are thinking about that right now. It's going to be 2 times 0 plus 4i over n. Okay, and that'll all be plus 9. That's the correct actual notation, showing that it starts at 0. So you're adding that 0 to the ith jump. And then it would foil, well, not foil, but it would simplify out to show you that this one is going to be, let's see, we're doing 7 is A. It starts at 1. There's that starting at 1. And it's 2x plus 9. Okay, and yes, it has a jump of 4 because of this width right here. All right, so let's go to number 8, which is B. It has a jump of 4. There's the jump of 4. It starts at -1. There it starts at -1. And it's 2x plus 9. That's how you get this one. D, its jump is 2. So 1 to 3, that's a jump of 2. It starts at 1. And it's x squared plus 9. Here's the last one. The width, or the jump, is by 2. There's a 0 plus 2i over n to be interpreted. So it's starting at 0. And then it's 2 stuff plus 9. Otherwise, 2x plus 9. And that's how you do those, guys. Okay, so yes, I will extend the homework out, and most likely what I will do, since your quiz is tomorrow, is I will extend this homework, whether it's on WebAssign, I think it's on Delta Map. I will extend the due date until, let's see, tomorrow's Wednesday, until Friday. So you have until Friday to complete this if you haven't already done so, since I'm just now putting out the video. But I hope this video works. Or I hope it helps, and you should be fine now, knowing how to do those summation notations with those infinite limits, as far as finding the actual exact area, but in that summation notation. All right, I'll see you in class next time.